All right, I have on the board a resistor, and what I want you to do is to give me the value of the voltage across the resistor and the polarity of that voltage. So I'll give you about 2 minutes to work the problem out. Give me the voltage drop across the resistor with polarity. About 2 minutes. You can see the board, can't you? Can you guys see the board?
Yeah, the equation shows up.
Okay. So you got a resistor, 2 ohms, 15 amps to the right, 10 amps to the left. Give me the voltage drop across it with polarity. I'll give you about 2 minutes.
Hey, Professor, your mic's off.
Okay, so the voltage across the resistor, did anybody get it? How much is the voltage?
I got 10 volts.
10 volts. Okay. What's the polarity of that voltage? Is the positive on the left side of the resistor or is the positive on the right side of the resistor?
It should be on the left side of the resistor.
Yep. So here's the polarity, and here is the voltage drop. Now the reason,
And this is a side question because there's 2 different ways of drawing circuits, 2 different ways of showing the direction of flow. There's the common flow and I can't remember the terms, but one moves from negative to positive, the other one moves from positive to negative. It just depends on which mindset you're using. If we were not using conventional circuit, we would flip that
yeah,
in this situation.
no. if you were using conventional current flow, you would show the net current going this way, going from right to left, and you would show it entering the negative side of the resistor and leaving the positive side of the resistor. I
So it
never
would just be a
ever
negative voltage.
say again.
Would it be a negative voltage in that case? Would it just show?
Well, it depends on which way you make your measurement, but I don't ever want you guys to do that. Never use electron flow. The only time in this school you'll use electron flow is when you're taking, well, if you're electrical, I don't think electromechanicals take electronics, but if you take electronics course, that'll be the only time you use electron flow. I don't want to go into the reason why right now. You can ask me maybe during lab. But as far as the polarity of the voltage, it depends on where your leads are when you're measuring the voltage. If your positive lead is here and your negative lead is there, then we'll read a negative voltage. If you reverse it, will be positive. Let me not get too far off track. Who gave me is that Ben? Is that you talking?
Yes, sir.
How did you get to 10 volts? Tell me what you did. What was your thinking process?
I took the difference between the amps, just kind of like we did with not the Thevenin circuit, but with the Wheatstone bridge, the Wheatstone bridge,
Exactly.
and took the difference, and then multiply the difference in amperes by the resistance.
Okay, and that's exactly right. So just to kind of back up on that a little bit. So what he did, guys, was he said, all right, I know I have 15 amps of current flowing to the right. I got 10 amps of current flowing to the left. The actual current flow in this resistor is the difference between the two. The actual current flow is 5 amps. If I know the direction and magnitude of current through the resistor, I can just use the current times the resistor value to get the voltage. If the current is 5 amps, if the resistor is 2 ohms, the voltage across the resistor has to be 10 volts. So we got 10 volts. And what we said was, by definition, we always use conventional flow. For us right now, that's the only thing that exists. And with conventional current flow, the side of the resistor that the current enters, by definition, is positive. The side of the resistor that the current leaves, by definition, is negative. And so we have this polarity, plus, minus, and this is exactly right. I want to show you something else. I want to show you another way to get the same answer. You kind of already know this, but I want to show you something here, and this is going to lead us to something else. Instead of finding the net current through the resistor, which is probably the most natural way to do it, but instead of doing that, here's what you could do. You could say, I'm going to act like that 10 amps doesn't exist. I'm going to act like the only current in the circuit is 15 amps. And that 15 amps is flowing from left to right. If that 15 amps were the only current that exists, then using the same equation, the volts across that resistor would be 15 times 2 would be 30 volts. So I would have 30 volts across the resistor, and the polarity would be positive on the left, negative on the right. You're not going to say, all right, I'm going to act like the 15 amps doesn't exist. The only current now that exists is the 10 amps. If the 10 amps were the only current through the resistor, then using the same kind of logic, the same equation, we should say 10 amps, I would take the current times the resistance. Using this equation, I get 20 volts. This time the polarity is positive on the right, negative on the left. Now, if my polarities were like this, if I had 30 volts, 20 volts, positive, negative, positive, negative, we call that series aiding, and in that case, I would add them up and get 50 volts total. In this case, that's not what I have, it's the opposite. I have positive, negative, but this is positive on the right, negative on the left. So this is what we call series opposing. And what I got to do is subtract them. When I subtract them, I get 30 minus 20 is 10. I keep the polarity of the bigger voltage, like that. So again, I get 10 volts, just like I did over here. And what this shows is this. You can find the net current in the circuit and get the voltage drop across the resistor. And once you got that voltage drop across the resistor, you can get power, whatever else you want. Or what I did over here, we took each current independently, found the voltage for just that current, and then we combined them. If the polarities were in a series aiding fashion, we added them up to get the total voltage. If there were series opposing, we took the difference. In this case, there were series opposing. And you see we got to the same answer by considering each current independently. And so that's kind of where we want to go for a couple sessions in this as we go through. Now, we're at the point now where you guys can solve circuits, series circuits. You should be able to solve a series circuit, parallel circuits, and series parallel circuits. But now what I like to do is add more voltage sources to the circuit. How would you solve a series parallel circuit with multiple voltage sources? If the voltage sources happen to be in series with each other, say I have one like this and like this. Say this is 10 volts and this is 10 volts. Well, that would be let me make this 15 volts. That would be a pretty easy analysis. All I have to do is combine these into one, replace this with a 25 volt voltage source. Or if I flip one of these over, I'll take the difference. I replace these two with a 5 volt voltage source. It's not an issue. But if I have a connection where the voltage sources or current sources are not directly connected to each other, that's a whole other problem. So we're going to spend the next probably the next couple of weeks learning different ways to solve circuits with multiple voltage sources. And what I just demonstrated here, showing you that you can consider each voltage source independently, or in this case, each current independently to solve the problem, is called the method of superposition. I want to talk about that. Now, if you have your handouts from Blackboard, get the one out that has the Wheatstone bridge on it. Because there's a problem at the bottom of that page that I want to use as an example problem. So if you get the sheet out with the Wheatstone bridge on it, topic 2 on that sheet, there's a circuit we're going to use that as an introduction to the superposition theorem. So get that out, and you might want to draw the circuit on the sheet of paper. And what I'm going to do is walk you through how you would calculate values if you have multiple voltage sources in the circuit using the method of superposition. Go ahead and get the paper out. I'll put the circuit on the board just in case you don't have the paper, and then we will proceed. All right. So this is the method of superposition. Superposition. And what, in my own words, what superposition says is, if you have a circuit with multiple voltage sources or current sources, If those voltage sources are not connected directly in series and you want to solve the circuit, what you can do is solve the circuit by treating each source independently in the circuit. Then you want to combine the quantities at the end for your current or voltages. If your currents are going in the same direction, you would add them. If they're going in opposite directions, you would subtract them. If your polarities on your voltages across a resistor or element are both the same, then you would add them. If they're opposite, you would subtract them. In that case, it would be series opposing. We're going to treat each source independently. What I mean is we're going to solve the circuit as if, say for this circuit, VS1 was the only source in the circuit. And we'll get the values for whatever we're looking for. And then we'll turn VS1 off and leave VS2 in the circuit, and then solve the circuit, and we'll combine the results. So what we do with superposition is basically no matter how many, we'll just say voltage sources we have in the circuit, we turn all the voltage sources off except for one to see what effect that one has on the circuit. We turn that one off and turn the other one on, see what effect that one has on the circuit. Then we combine the results, understanding that if I have currents in the same direction from two different sources, we will add them. If I have currents in opposite directions, we will subtract them. If I have voltage polarities that are the same, I would add them. If I have polarities that are different, we will subtract them. So it's easier just to kind of walk through an example and kind of explain it as we go, and that's what I'm going to do. I think you guys will get it. The method is pretty simple. It's very, very intuitive. So what we got to do in this circuit, what are we looking for? We want to find the current in this resistor, the current in R2. So the way we're going to do this is we're going to solve the circuit basically twice. Once with only VS1 in the circuit, we'll turn VS2 off, see what current we get from VS1. Then we'll turn VS1 off, turn VS2 back on, see what current we get from VS2. If those currents, individual currents, are going in the same direction, we're going to add them. If they're going in the opposite directions, we're going to subtract them. So we'll walk through. Now, how do I turn a voltage source off? Well, you do that the same way you turn it off when you were Thevenizing. When you want to remove a voltage source circuit, what you do is you replace it with a short circuit. So here's what I want you to do. Take out a sheet of paper, draw this circuit on the paper. And what I want you to do is turn VS2 off by replacing it with a short circuit, and then find the current in R2. And then we'll stop, we'll come back, revisit this to make sure we all get the same answer. So you're gonna, I like to just redraw this. I'll just go ahead and redraw it for you. So what you're gonna do is we're gonna consider the circuit with only VS1 in the circuit for right now. We're gonna turn VS2 off. The way you turn the voltage source off is by replacing it with a short circuit. So here's what that would look like. All right, so what I want to do is solve the circuit with only this first voltage source in the circuit. So I got to turn VS2 off. I turn the voltage source off by removing it, replace it with a short circuit. So I'm going to take this out, and I'm going to replace this with a short. I'm going to figure out what the current is in this resistor with only VS1 in the circuit. So I'm going to pause. I'm going to let you solve this circuit. Do your analysis that you've been practicing for the last couple of weeks. Give me the current in R2. I'll pause for a second and let you calculate that. All right, so solving this circuit, turn VS2 off. I want to see what current contributions I get from VS1, the 10-volt source. I'll turn VS2 off. I replace it with a short circuit. I have a series parallel circuit. I'm now going to solve it with current in R2. So we just use our technique that we learned before. Got this node right here. I'll just call that A. And what happens when I turn VS2 off, it puts R2 and R3 in parallel. These two resistors are in parallel, so I can redraw this circuit. I don't really have a lot of room, so I wonder if you guys can see. I don't know if you can see if I draw it up here. Basically, I have these two in parallel, so what I end up with is this. Got the 10-volt source. These two in parallel, I got R1 still of 100 ohms. But these two in parallel, I have 100 in parallel with 100 gives me 50 ohms. And the way I got that, you can use the product over the sum rule. You can use the 1 over R rule. But the easiest way, since both resistors are the same, you take one resistor, divide by the number of resistors that you have. There's two of them. That gives me 50 ohms. So I got 50 ohms. And this node A now is right here. Node A. And so what I got to do is solve this circuit for the voltage across node A. We can use voltage divider rule for that. I use the voltage divider rule. Let me go to another colored marker. I want to know, basically I want to know the voltage across the 50 ohm resistor. The voltage divider rule says, take the resistor I want to know the voltage across, put that in the numerator, divide by the total resistance in the circuit. I got 100 in series with 50, that's 150. Multiply that fraction by the total voltage, 10 volts. And that'll give me what I'm looking for, which is the voltage across node A. So what is that? That's 1/3 of 10. 10 divided by 3, somebody do that for me. What is 10 divided by 3? 3 point what?
3 continuing.
All right, so somebody said it was 3.33 and it continues from A to ground. So I have 3.33 volts continuing from A to ground. So that means that since both these resistors are in parallel, they both get that 3.33 volts. So now that I know the voltage across R2, I can easily find the current in R2 by taking the voltage, which is 3.33 volts, divide that by the resistance, which is 100 ohms. It's going to give me 0.0333 amps, which will give me about 33.3 milliamps. Anybody agree with that? 33.3 milliamps. You guys see how we did that? I have 33.3 milliamps. That's a contribution from VS1, the turbo source. I have, in this direction, from this voltage source, 33.3 milliamps. So now what we got to do is the same thing. We got to figure out the current contribution and the direction of that current from VS2. We'll do that and turning VS1 off, doing the same analysis with only VS2 in the circuit. So you want to go ahead and
question, because I got 66.7 milliamps, and I'm trying to figure out where I went wrong. Because I did 150 ohms for the total resistance, and then I divided the voltage by the resistance, and I got 66.7 milliamps.
Did you use the voltage divider rule?
No, I did IT is equal to VT over RT.
All right. Well, if you do that down here, you found the total current.
I was looking for the total current, and the total current I got was, oh shoot, I skipped ahead, and that's why you got 33.3 for R2 for branch R2.
Yeah, we got 33.3 milliamps. What did you get?
Okay, I'm on the wrong section of the branch. I got 66.7 for R1 amps going across to R1, which would make sense. So I recant my question.
Okay. Everybody see what we did? And we agree with the 33.3 milliamps? I think it's correct. So now what this method does is, of course, assumes that you mastered with series parallel calculations. If you're a little rusty with that, you may have a little bit of trouble. I think if you go through here and just apply the method that we talked about, or we practiced, and give me the same thing for VS2. Turn VS1 off, VS2 in the circuit, redraw the circuit, and then calculate the current in R2 from this voltage source in the circuit by itself. So I'm going to pause and let you do that. And while you're doing that, I'm going to clean the board up. I see some of you have already sent me your attendance. Go ahead and do that. I always forget to tell you guys to do that. Some of you are on it. You remember on your own. So I want to solve for only VS2. I'm going to turn VS1 off. Replace it with the short circuit. I put this wire here to short this out. That's going to make R1 and R2 in parallel. So this forces those in parallel. And I got this node right here. I'm going to solve for that node voltage and then use that node voltage to give me the current. So there's your circuit you want to solve. I'm going to redraw the circuit to get my equivalent series circuit. This right here is R1 in parallel with R2. Both those are 100. So again, I have 100 in parallel with 100, which gives me 50 ohms. So this equivalent resistance is 50 ohms. Connected to R3. It's 100 ohms connected up to this voltage source, which is 5 volts. This node A, the circuit right here. So I want to figure out the voltage from node A to ground. That'll tell me the voltage from node A to ground across R1 and the voltage from node A to ground across R2. So go ahead and get that voltage. You can use Ohm's law in this circuit, or voltage divider rule, whichever you like. I like to use the voltage divider rule because it's a little less work. I'm going to go ahead and do that. Voltage divider rule says if I want to know the voltage across a resistor, put that resistor in the numerator. Divide that resistor by the total resistance in the circuit, which in this case is 150. Multiply that fraction by the total voltage, which in this case is 5. And that'll give me the voltage drop for VA. Somebody tell me that's 1/3 of 5. 1/3 of 5 is what? It'll be half of that number. What is 1/3 of 5? 5 divided by 3.
3.33 continuing.
Got 3. You know what we got before?
Yes, and wasn't it also 50 over 150 for the same?
Yeah, but we multiply by 10. This time we're multiplying.
Oh, sorry, I didn't multiply the 5. I apologize.
Okay, so what's 5 divided by 3?
1.66 repeating.
Okay, so we got 1.66 repeating volts. That goes from node A to ground. That means across this resistor that we're interested in, we got 1.66 volts, node A to ground. So now we can get the current in that resistor. Now, here's where your color coding comes back into play. When you're using superposition, Normally we keep, when we're doing analysis, we keep all of our currents the same color, all of our voltage drops the same color, and so forth. When you use a superposition, you want to use different colors for current because we're interested in, are those two currents or three currents, are they going in the same direction? If they are, we're going to add them. If they're going in opposite directions, we're going to subtract them. Our color coding, it just makes those currents stand out. So I'm going to use, I'll use blue for my current. So this current is going to be this voltage divided by the resistance. I'm going to end up with 16.66 milliamps going down. So over here in my original diagram, I made the current from VS1 in red. I'm going to make the current for VS2 in blue. Going down, I have 16.66 milliamps from VS2. My actual current in that resistor, since both these currents are going in the same direction, the actual current would be the sum of the two. What would that be? Is that 50 milliamps? I think it's 50. Pretty close to 50 milliamps. 33.3 plus 16 point, yeah, that's about 50 milliamps. So my actual current in this resistor is 50 milliamps going down. So that means my voltage polarity across it is like this. The actual voltage, if I want, they didn't ask for voltage, but if you want it, would just be the current times the resistance. I can get the voltage. At this point, I can get the powers. I can do whatever I want. So here we solved a circuit with multiple voltage sources using the method of superposition. Now I got two things I want to point out before we end the session. At the bottom of the handout, it says more practice. It says determine the current in R2. The polarity of VS2 is reversed. What will happen if I take this battery and I flip it over? So you don't really have to do much work there because what's going to happen is all your analysis will be the same. The only thing that will be different is this current, instead of going down, instead of going in the same direction as the 33 milliamps, it's going to go up. If I reverse this voltage source, and instead of adding the currents to get the 50, I will subtract those two currents to get the net current in R2. That's the first thing. The second thing is it's important to just kind of understand. When I use superposition, when you calculate power, you cannot calculate power individually. And here's what I mean by that. You can't come in here and say, all right, I'm going to find the power in R2. I'm going to find the power dissipated by R2 with just VS1 in the circuit. So you do I squared R. I'm going to find the power dissipation from only VS2 in the circuit. I'm doing I squared R. And add those power. That won't work. The reason is power is not linear. This only works with linear functions, linear equations. The power curve is not linear, as you'll find out. Well, you guys didn't do the power experiment yet. We're supposed to do that, but I didn't have all the parts for it. But next week when we do the power lab, you'll see that power is not a linear function. Superposition works with linear functions. By linear function, what I mean is if you make a graph of the quantities, you get a straight line. You don't get that with power. Therefore, you cannot use superposition with power. If you want to find power, you get the power at the end. When you find the net current or net voltage, then you can use that net value to find power. But you cannot find power individually and then combine the powers. So make sure you understand that. So we've done this example, and I don't think we can do another one. Well, we probably could, but it's Friday. What the heck? I'm going to post some practice problems because the next homework is a combination of this, a combination of superposition and Thevenin. We're going to put the two together to solve problems. So you got to know how to Thevenize, which we practice that. We've only done this one superposition problem. So what I'll do probably won't be today, but between today and tomorrow, I'll post a few more practice problems with answers. And what I want you to do is between now and Monday, practice using superposition. If you get stuck, if you have any questions, ask me on Monday. Then Monday, we're going to proceed to combine superposition, and Thevenin to solve problems, and then your next homework is going to be based on that. The superposition Thevenin homework. Does anybody have any questions for me before we end?
I have a question, but I'll wait because it's more unrelated to our subject matter.
Okay, that's fine. Anybody have any questions regarding superposition or any other technical type question that we need to discuss before you enjoy your weekend? It's going to be warm today. It's going to be in the mid-50s, so it's really nice out there. So get to enjoy your weekend and not freeze to death or burn up. It's not going to be too hot. It'll be just right. Yeah.
I think this one, it was a little bit complicated because to cut off the second work one part and another part, I would suggest you to send it to us so we can watch it more time. Maybe
Okay.
I can understand.
Okay. Yeah, I can do that. So what I'll do is, he's saying he wants to be able to go back and look at the video. I agree with that. It is a little confusing at first when you first see it. So I will, I'll upload that to YouTube and I'll send you the link. If you're in section 2, you'll have access to this video. And I'll do that today. That's a good suggestion, Jonathan. Thank you.
Yes, just do that because it was a little bit complicating. So to do like this, it's okay. But if I'm staying alone, I'm gonna forget all the part that you do it. That's what I'm saying to you.
All right, so I'll do that. I'll make sure you get the video link.
Yeah, I'm section 2.
Okay. So guys, in section 2, you'll have that before the end of the day. Any other questions or comments? Guys, have a great weekend. If you need me for anything, please send me a text. I'll be available through text. And I'll see you on Monday.
So I was just wanted to pick your brain just a little bit since you're more of a physics guy. Was this more named out in nod to superposition coming from theoretical physics, or is there a little bit more where they actually used the superposition concept out of quantum that inspired how the circuit was made?
I think this came before any quantum stuff. Superposition applies not only to circuits, it applies to a lot of different kind of phenomena. Like you can use this with mechanical vibrations. You can use this in a lot of areas. So I was surprised to find that out. I studied engineering before I studied physics. I learned about superposition in engineering and thought it only applied to circuits. I later learned that it applies to a lot of different phenomena. So in physics, we use it. If I have, say, for instance, I have multiple vibrations on some kind of system, some kind of vibrating systems, I can actually consider each variation or vibration by itself and use this method to solve for whatever I'm looking for, the net value. My point is that superposition, I'm assuming you found areas in quantum physics where this applies, but this applies across a lot of different areas and subject matters and all of that.
That's fascinating. Because I actually got to engineering because I found a couple of books on quantum. So like The Perfect Theory and just a few that kind of went through the history, and the theories were just so fascinating and interesting. And I was like, oh, engineering, that's kind of like the practical use of physics and calculus. So great, I can make a job out of it.
Well, what you could do, I kind of was the same place I was actually. I wanted to go to medical school. I thought I wanted to be a doctor, so I went to a special school where we studied biomedical science for high school, actually from junior high school through high school. Then I had this teacher that went to engineering school, didn't finish, and he ended up teaching a subject in high school, and he had a lot of influence on me. I didn't even know what an engineer was, but I wanted to be a doctor. And so I went into engineering, and while taking those technical courses, that's what got me interested in physics, because I found myself, this stuff, while okay, it's kind of boring to me, to be honest with you. And I'm wondering, like, all right, this is cool. Like, I understand that voltage is kind of the force that makes electrons. But what really is a voltage? I would ask such detailed and fundamental questions that the professors would tell me, look, Ron, you need to go study physics. So I went and studied the engineering, and I went back. This got me interested in the physics. So I wish I could have went further than I did, but at some point you got to get a job and support a family and all of that. But yeah, this is cool because you can make stuff happen. But man, I think physics is where it's at. You really want to lean.
You start getting down to like the nitty gritty, and you start you figure out it's like, okay, well, it was actually kind of the same thing with preaching of like you actually figure out when you're talking about one thing, you're actually talking about a completely different subject. So that kind of go universally. So like from my background, a big one is like, when does life begin? Like when does the soul begin? Or free will versus determinism. Do we live in a deterministic society, or does free will exist? Is it not? Like there's certain things that in that question, especially deterministic versus free will, that definitely comes straight back to physics because that's going to change your calculations.
Comes to physics, in that comment, I hear physics, I hear philosophy, I hear there's a lot, and I think you and I mentioned before that they say at the highest levels you can't tell the difference between physics, theology, mathematics. They all kind of converge, and that's really exciting. You start to think about the soul and like what is thinking if we're mechanical beings, what is thinking? Is it really does exist apart from? I mean, you and I just need to have a conversation.
Absolutely, because that's so cool. Of when you go in deep enough anywhere on almost any subject matter, you're going to reach what I'm defining as the edge of human understanding. And there is an edge, and it's almost like kind of the edge of the universe. Is if you go in a line far enough, if you teach yourself enough, you're going to get to a point where you realize that no one knows shit, and we're all just doing the best that we can with the best that we can.
And there's a certain excitement in what you just said, and also a certain beauty in what you just said. I mean, it's amazing. It really is.
That's awesome. I love how you actually use that term too, because it was actually through a lot of the concepts through physics and that I began to actually look for beauty in all sorts of aspects of life. Beautiful equations, beautiful ideas, and we limit this concept to the physical very often, but then there's a certain point where the physical stops making sense. When you realize, like when you get down to a certain level of physical doesn't mean anything. Right. We are just certain types of energy that have found a way to cross together in a very specific way that makes kind of what we see and something that we can kind of understand. But what we can physically understand, this reality, is less than a third of what exists in all likelihood, maybe even less.
Mm-hmm. And the reason, because science speaks to only what we can measure. And the fact that what you just described, there's no way to measure it. So I'm not going to say scientists don't believe, but it's not in the realm of science to even discuss what we're talking about right now.
Yeah.
So, maybe that's why you need theology. I don't know.
That's actually the place I've gotten to is no matter who you are, what you believe, you have an edge of your understanding. There is a limit. And our human nature is to push beyond that and to fill in the blanks. And so no matter what you believe, if you call yourself atheist, if you call yourself agnostic, Catholic, Christian, Buddhist, every single individual that is alive and sentient has a religion, whether they realize it or not.
I agree. Even if you're atheist, you believe in something, don't you?
Yep, because it means how you live, and it fills in gaps that you are not qualified to answer. Right. Anyway, absolute pleasure chatting with you as always. I cannot.
I tell you what, Ben. One day maybe we can grab lunch somewhere or something. I don't know with this virus, but we'll get. Are you taking AC or not?
Oh, 100%.
Okay, I'm hoping you take it with me. I don't know. Hopefully our names will be on there on the 3rd. I don't know what I'm teaching.
I need to set up a meeting with Professor Feist, Larry Feist. And so I'll specifically just try and see if I can get into that class.
Okay. And if not, then we'll get together. We'll get lunch and we'll do something. We can just talk. We'll have some time to talk.
And yeah, the other reason I actually was very excited about going back to school is just realizing the network capabilities, the network opportunities, just because if you want to be intelligent, the best thing you can do is make friends and make friends with people who know about
Right,
something.
surround yourself with intelligent people, right?
Yep, absolutely. I've definitely come to the understanding that every individual has something that I don't know, and if you come into that concept of I'll offer what I have to offer, and I'll definitely accept whatever you have to give me, and just those interactions, we can just skyrocket with our education and how we learn to teach ourselves. Thank you for taking the time. I greatly.
I'm excited. We'll get together. We'll talk some more, and I still want to see those house pictures at some point.
Sounds good. All right, have a great rest of your day and weekend.
And Nathan, you have a question? I see you got your hand up in there. Nathan, are you able to talk or not?
Hey, Professor, is this going to be on YouTube?
Yeah, that's what Jonathan was saying. He wants me to put it on YouTube. So I'll put it on YouTube. I won't be able to do it right now, but I'll do it sometime by the end of the day. I'll put it on YouTube.
Thank you.
And I'll send out an announcement when I get it up there, okay?
Okay.
All right, buddy. See you later. Thank you.